Okay, we are live. Welcome to Math with Doug. We are doing some polynomial stuff. The dog is not here. Mocha is busy upstairs doing her other job, which is to be a heating pad when someone is sick. So Bunny is not feeling well and she needs a nice warm dog on her lap, and that's what the dog is doing. This is an Ajax jersey. Ajax, spelt Ajax, but in Holland, in Amsterdam, where this soccer team is from, they pronounce it Ajax, I think. And let's get into the math. Now, I was looking at a polynomials clue game, which I think some of you might have seen, and I found it kind of interesting. It had a really good mixture of all sorts of polynomial stuff. Some of the things that we have been covering in the past week or two, and some other things that I don't think we've covered yet. So it's heavy on the factoring. There's quite a lot of factoring. There's quite a lot of FOIL. So I thought I wanted to get into just some of the things that I saw in the clue game and teach the stuff that goes with that and not try and get too deeply into anything new. Now, common factor, I don't think I remember talking about that last week. So I think this might be new, at least for me teaching it. It's new teaching it to this crowd. What is common factor? It means that the terms in the polynomial have a common factor. We figure out what the common factor is and then we factor it out. So I'm going to show how to do that with these examples, and then I have another example as well. Now this is very similar to something that we already have done a lot of with numbers before we encountered polynomials, before we were dealing with variables. We think of a greatest common factor, for instance, when we are reducing a fraction. So factors and multiples are something we learn at a certain level in math, and then they keep coming back and being useful. When we get to fractions, the factors and multiples become useful again, and we use them a lot. And now we get to polynomials and we start doing common factor, which is even called factoring, and the knowledge we already have about factors of numbers becomes very helpful. In fact, we're going to use it here. So let's get into our first example. We have this polynomial. It's a binomial. It only has two terms. We have 3x squared plus 6x cubed. We're looking for the greatest common factor. But because it's polynomials, we have to sort of look at the numbers and figure out what their greatest common factor is. But we also have to look at the variables with the exponents and figure out what their greatest common factor is. And the answer, the greatest common factor we will find for these two terms, is going to be a combination of the greatest common factor of the numbers and the greatest common factor of the variables. Whew, that took a while to say. Okay, so let's look at the 3 and the 6. The greatest common factor of 3 and 6 is 3. So we're going to be able to factor a 3 out of this expression. And I'll write the 3 right away. Then we look at the variables with the exponents, x squared and x cubed. It's not as quick to do, but we're really doing the same thing. We're saying, what's the greatest common factor of x squared and x cubed? Meaning, what term can I divide both of them by? And the greatest common factor of x squared and x cubed is x squared. We can factor an x squared out of an x squared. X squared divided by x squared equals 1. So it fits. But we can also factor x squared out of x cubed because x cubed is bigger and x squared fits within it. X squared is a factor of x cubed. X cubed divided by x squared is x. We're subtracting exponents, so we're using some of the things that we've been working on over the past few weeks. Let's finish this question then. I'm going to put a line here to separate this one from that one, which is a separate example. The greatest common factor of x squared and x cubed is x squared, so that I'm also going to be factoring out of it, meaning I'm dividing it out of it. So then I say to myself, now that I've figured out what my greatest common factor is, what is 3x squared divided by 3x squared? And I'll write the answer inside the bracket. 3x squared divided by 3x squared is 1. Okay. We basically factored out everything there was, but it doesn't mean we have a 0 left. We're dividing. 3x squared divided by 3x squared is not 0. It's equal to 1. So we have a 1. Now we're doing this. 6x cubed divided by 3x squared. It's good to do it in pieces if you have to. 6 divided by 3 is equal to 2. And x cubed divided by x squared is equal to x. So the factor that we get when we divide 3x squared out of this expression is 1 plus 2x. And we have successfully factored this expression. We can't factor it any further. These factors are prime. Okay, let's try this one. That's my next one. What if we have a trinomial instead? Can we still do this? Yes. One of the things that's interesting about common factor is you can do it with a binomial, a trinomial, a 4-term polynomial, a 5-term polynomial. It doesn't matter how many terms are in your polynomial, it's possible still to do common factor. So when you're looking at an expression and someone asks you to factor it, you're trying to figure out what type of factoring method should I use, common factor might apply with any of them. So it's a good one to try first, actually. So, what is going to be the greatest common factor of 3x squared plus 6x cubed minus 3? We notice that there's a big similarity between my two examples. They both have 3x squared, they both have 6x cubed. So therefore, maybe I can factor 3x squared out as the greatest common factor. But no, that's not going to work because this last term here just has minus 3. It doesn't have any variables or exponents. So I'm not going to be able to factor the x squared part out. But if I look at the numbers, 3, 6, 3, all of these have a common factor of 3. So like I started with this one, I'm going to be able to factor out a 3. Then I look at the variables and I realize I'm not going to be able to factor out any x's or x's with exponents because this doesn't have any x's. So that means that the greatest common factor of these 3 terms is 3. And that's all I can divide out of it. 3x squared divided by 3 leaves x squared. 6x cubed divided by 3, do it in pieces, 6 divided by 3 is equal to 2. And x cubed divided by, oh, the x cubed is still there because I wasn't able to factor out any variables with exponents. So like the x squared stays here, the x cubed stays there, but the numbers I'm able to factor. And finally, minus 3 divided by 3 is equal to minus 1. Watch the sign. When you have the minus sign, it goes with the term right after it. So when I factor a 3 from minus 3, I'm going to get minus 1. The minus sign's still there. And I have successfully factored another polynomial using the common factor method. And I have proven that yes, if it's a trinomial, you can still do this. Here's another trinomial. And again, it starts with 3x squared. And again, it has plus 6x cubed. But this time, it has minus x to the 4. Yes, that's a minus, but this one doesn't have any number. It does have the variable with exponent. So kind of the opposite thing that happened here is going to happen there. This time, we're not going to be able to factor out the 3. Because we can take a 3 from this, we can take a 3 from this, but we can't take a 3 from that. But this time, all 3 terms have an x with the exponent. We have x squared, x cubed, x4. And we're asking ourselves, okay, what's the greatest common factor of x squared, x cubed, and x to the 4? And it's going to be x squared. Kind of like what happened here. The x squared fits within x squared, it fits within x cubed, and it fits within x to the 4. So we can take out an x squared. Then I'm going to put my brackets, and I'm going to do my dividing. 3x squared divided by x squared leaves just the 3. 6x cubed divided by x squared. The 6 is still there, but one of these x's is still there. X cubed divided by x squared is equal to x. And now this one, it's going to have a minus sign. X to the 4 divided by x squared. When I divide with exponents, we subtract the exponents. X to the 4 divided by x squared is equal to x to the 4 minus 2, which is x squared. I have factored this one. This time no number came out in the common factor, but a variable with exponent did come out. This time no variable with exponent came out, but a number did come out. This time both a number and a variable with exponent managed to come out. It really depends on what you have in the expression you're given, which of these assortment of things is going to happen. But the common factor strategy is still the same. We're looking for the greatest common factor of all the terms in the polynomials, and then once we figure what that is, we write it down and we divide the entire polynomial by that greatest common factor to figure out what the other factor is going to be. And I want to show that yes, you can have more than 3 terms. You can have a bigger than a trinomial and still do common factors, so I'm going to do another example. Okay, what's this one? I'm putting a 5-term polynomial. 2x to the 5 minus 4x to the 4 plus 6x cubed minus 2x squared plus 4x. 5-term polynomial. Now, I need to look for the greatest common factor, and I have variables and I have numbers, so I do it in pieces. I look at the numbers first. There's a 2, there's a 4, there's a 6, there's a 2, there's a 4. All of them are even numbers. All of them have 2 as a factor. I'm going to be able to take out a 2. But I also have to look at the variables. We have x to the 5, we have x to the 4, we have x to the 3, we have x squared, and we have x. What's the greatest common factor of all those 5 things? It's going to be x. We can take an x out of any of those, but we can't take an x squared, for instance, out of that. X squared is bigger than this. Doesn't work. So all I can do is take out an x. At this point, I feel I have figured out what my common factor is. I'm going to write my bracket, and I have a bunch of division to do. 2 divided by 2 cancels. X to the 5 divided by x is x to the 4. Here's a minus sign. I'm going to write it down. 4 divided by 2 is 2. X to the 4 divided by x is x to the 3. Remember, when we do these divisions, we are subtracting the exponents. 5 minus 1 equals 4. 4 minus 1 equals 3. And yes, also remember, when you just have an x, that means you have x to the 1. You don't have to show this exponent, but you can. And that's the exponent that you're using when you do that subtraction while you're doing a division. 6 divided by 2, it's positive, so I'm putting a plus. 6 divided by 2 is 3. And x cubed divided by x is x to the 3 minus 1, which is x squared. Here's a minus sign. 2 divided by 2 cancels. X squared divided by x is x. X to the 2 minus 1. That is x to the 1. I could write the little one, but I don't have to. Here's a plus. Then 4 divided by 2 is 2. And x divided by x cancels, so I don't have an x and a variable to show here. My bracket is too far away. I didn't really expect that, so I'm just going to move my bracket a little closer. I have finished. I end up with a 5-term polynomial as one of my factors, and this monomial as one of my factors. And what can we do to verify? Okay, one of the greatest things about factoring is that it's easy to verify. It's easy to check your answer. If you already know how to multiply polynomials, which we do, then we try multiplying the factors together and see if we get the expression we started with. If we did, then it means we must have factored it correctly. 2 times 1 is 2. X times x to the 4 is x to the 1 plus 4, which is x to the 5. 2 times negative 2 is negative 4. X times x to the 3 is x to the 1 plus 3, which is x to the 4. 2 times 3 is 6. X times x squared is x cubed. 2 times negative 1 is negative 2. And x times x is x squared. 2 times 2 is 4. And x times, there is no variable there, is equal to x. Another way of saying that is x times 1 is equal to x. If you're wondering, what am I multiplying by? There's no variable here. You can say, well, then I guess I must be multiplying by a 1 because it works. X times 1 is x. And that, hey, look, our 5-term polynomial that we got as a result of our multiplication is the same one that we started with. Looks good. We're able to verify. With factoring, we're always able to verify by multiplying our factors together and see if we get the expression we started with. And that's really great because if you're ever in a position where you have to do this and you don't have any access to find out if your answer is right, well, yes, you do. You just do your verification, you do your multiplication, and you find out yourself if your answer is right. It's great to have that power. Okay, my next topic is another factor, I'm checking the time, is another factoring method called difference of squares. Very useful factoring method. Not a very difficult one. But to introduce that idea, I'm going to do a review of something we were covering a lot last week, the FOIL. Now the FOIL is involved in a lot of our factoring, even though FOIL is really part of multiplication of polynomials. When we multiply two binomials, we use the FOIL. Well, when we factor, and our factors are going to end up being two binomials, it's kind of like we're doing the FOIL backwards. This forwards backwards stuff happens a lot in math. So I'm going to erase this topic title. I'm going to erase this big example. I'm going to write in the name of my new factoring method, difference of squares. Everybody loves squares. Now, what's great about this is it says exactly what it is. The words in this title kind of tell you what you're doing when you use this factoring method. But I'm not going to factor right away. I'm going to do a FOIL. I'm going to take an example, and I know I did a couple examples like this in the last lesson. Like x minus 5 times x plus 5. With the FOIL, first outside, inside, last, we start by multiplying the first terms in the two binomials. X times x is equal to x squared. Then the outside terms. X times 5, that is plus 5x. They were both positive, so it's going to be a plus. Then the inside terms. Negative 5 times x, that's going to give me negative 5x. Negative times a positive gives a negative. 5 times x is 5x. Okay, that's good. Finally, the last, the L in FOIL is last times last. Negative times a positive is a negative. 5 times 5, 25. But of course, when we do the FOIL, we get our four terms and we check to see if we have similar terms. And sometimes you combine those similar terms, but sometimes this happens, which is that plus 5x minus 5x cancels. So now we have to write our answer as x squared minus 25. Well, whenever you multiply two binomials that are identical, except for the fact that one of them has the minus and the other one has the plus, this is going to happen. Because when you do the O for FOIL, the outside terms, you're going to get an answer that is the same answer as when you do the I in FOIL, the inside terms, except one of them is going to be positive, the other one's going to be negative, and then they're going to cancel. So x squared minus 25. What does this remind me of when I look at this cute little binomial? Difference of squares. Difference means subtraction in math. So there's a difference, it's a subtraction. Squares, what is a square in math? Well, we know it's a shape, but it's also a number that you get if you multiply another number by itself. So for instance, 3 times 3 is equal to 9. 9 is the square of 3. So that's another square. Well, x squared is a square because it's something you get when you multiply something by itself. When you multiply x by itself, that's x times x, that's x squared. X squared is a square. And 25 is also a square because when you multiply 5 by 5, you get 25. It's a square. So we have a difference of squares, and that is a factoring method. The factoring method almost doesn't need to be shown, but I will show it. We have x squared minus 25. When we do a difference of squares, well, first we have to realize that's what it is. Now remember what I said, I'd look at this and I might think, well, it's a binomial, but you maybe could do common factor with it, so I'll check. No, there's no common factor, so we're not doing a common factor here. But it's a binomial, and difference of squares applies to binomials, so that's the next thing I want to check. So that means I have to check first, is it a difference? Yes, it is. It's not a plus, it's a minus. Are they both squares, these terms at the beginning and end of it? Yes, x squared is a square, 25 is a square, it's a difference of squares. Therefore, when I factor it, I'm going to get two binomials as my answer, so I may as well draw the brackets. And what variable do I have to multiply by itself to get x squared? Yes, that's x. So that's going to go in the first position in both binomials. What number do I have to multiply by itself to get 25? Well, that's 5. That's going to go into the second position in both binomials. And then it's going to have to be a plus and a minus. Doesn't matter which one we put first. I could have said x minus 5, x plus 5, but the important thing is that I have to have one of each, one plus and one minus, because that is part of the situation that makes this happen. So if there's one plus and one minus, when I verify by multiplying this, the two middle terms are going to cancel. I don't really have to show the verification, do I? Because it's right here. Because my verification of this would look like this. So it is forwards, backwards, the same thing. When you multiply two binomials that are identical except for the sign in the middle, then the opposite of that is the difference of squares factoring method. This is cool. Difference of squares is fast to do because once you realize that's how it works, you just recognize it for what it is, write all the brackets you need for the two binomials, And then you quickly are able to fill in everything that you need, and you always get it right because the pattern works really well. Let's check that by trying some. I'm going to do one more right here. How about, not very different, x squared minus 36. It's a binomial. There's no common factor. X squared is a square. 36 is a square. That means I can do difference of squares. I write my binomial brackets. X squared comes from multiplying x by another x. 36 comes from multiplying 6 by another 6. I need to put one plus sign and one minus sign, but it doesn't matter which one I put first. So this time I'm going to put the minus sign first, plus sign after. I have factored it that quickly. And of course I can verify by multiplying. FOIL, first times first, x times x, that's x squared. Outside times outside, x times 6, that's plus 6x. Inside times inside, negative 6 times x, that's minus 6x. Last times last, negative 6 times positive 6, that is negative 36. But these two middle terms cancel. So to write it in its most simplified fashion, I have x squared minus 36. Same thing I started with. Difference of squares always works like this. Now you might ask, okay, does it always have to be a minus and a plus? What if we were two minuses? Does this still work? Well, no, it really does have to have a minus and a plus. And I'm going to show that by doing another example that's quite similar. Of course, I'm doing the FOIL here. I have two binomials. But what if they're both minuses? What happens? Will the two middle terms cancel out? FOIL, first times first, x times x, that's x squared. Outside times outside, x times negative 5, that's minus 5x. Inside times inside, negative 5 times x, that's also minus 5x. Last times last, negative times negative is positive. 5 times 5 is 25. The two middle terms will not cancel because they're both negative. So we have x squared minus 10x plus 25. This binomial with the minus thing didn't happen. Sure, that's a square, and this is a square, but otherwise it doesn't work in exactly the same way. So this is just a regular trinomial where we use the method of factoring a trinomial that we were doing so many examples of last week, and we will do some more examples of that this week as well. I have them on my other page, on the other side of this page. Okay, how am I doing through time? Pretty good. I want to do a few more difference of squares example stuff. So I'll erase this. And let's try a few more. What if, I love asking the what if question. What if I have 49 minus x squared? Kind of like the other ones, but this time the number is in the first position and the x squared is in the second position. Doesn't matter. It's still a difference of squares. We're really just checking whether this title applies to it. First thing I want to do is say, can I factor this with common factor? No. There's no common factor between 49 and a negative x squared. So now I want to think of difference of squares. Is this a square? Yes. I know my multiplication tables. I know 49 is a square. Is this a square? Yes. X squared is clearly a square. So I can do difference of squares. Write the two sets of brackets. What's the square root of the first term? The square root of 49, that is 7. What's the square root of the second term? The square root of x squared is x. I need 1 minus and 1 plus. I can put them in whichever order. 7 minus x, 7 plus x. It's kind of backwards looking compared to the other examples, but I did what I have to do when I do difference of squares. It seems to be working. Let's do the FOIL and verify with multiplication. First times first, 7 times 7, that's 49. Outside times outside, 7 times x, that's plus 7x. Inside times inside, negative x times 7, that's negative 7x. Last times last, negative times positive gives a negative. X times x gives x squared. Two middle terms are equal and opposite. They cancel. 49 minus x squared is the simplified way of writing this. That's what we started with. We verified. We get it. Didn't really leave enough room, so I'll erase, and now I'll do another one. So you realize how much fun it is even to just make up examples for this. I'll take one without taking it off of my clipboard. Let's do something fun. What's fun? x squared minus 144. Everyone remembers those days long ago when they learned the multiplication tables and they learned them up to 12 times 12 and how smart we all felt when we got to know very early in the process that 12 times 12 is equal to 144. It's so easy to learn that one because it's at the bottom corner of that multiplication table. Well, 144 is therefore a square. It's 12 times 12. X squared is a square. This is a difference. This is a difference of squares. Write my brackets. Square root of x squared is x. That goes in both of these places. The square root of 144 is 12. That goes in both of these places. We need 1 plus, 1 minus. We have it. Just as easy. Big number, just as easy. And if you know some other numbers that are squares that are even bigger, well, you can show off and you can make up an even more complicated looking example and still find it easy. To do that, to give an example of that, I'm not using this right now, to give that an example of that, I'm going to come up with an even bigger number, just to show off that I can do this, how fun it is and how easy it is to come up with an interesting example. I will erase. It's the biggest number I can square in my head without being afraid of getting it wrong. How about 35 times 35? Let's see if I can do this. 35 times 35. Well, I can break it down. So the 35, I can break that down into 3 tens and a 5. And 10s are easy to multiply by, and 5s are easy to multiply by. So 35 times 35 could be 10 times 35, 3 times, plus 5 times 35. I think I can do that. 10 times 35 is 350. But I need 3 of those. So that's 900, that's 1,050. But then 5 times 35, I have to remember that 1,050, and I don't want to write it down, I want to keep it in my head. 5 times 35, well 5 times 30 is 150, and 5 times 5 is 25, so 150 plus 25 is 175. So 175 plus the 1050 I had before, that's 1225. 12, let's see if I got it right. Is 35 times 35 equal to 1225? I feel confident that it is. Because I learned a trick somewhere that when you're squaring a number that ends in 5, a 2-digit number that ends in 5, like 35, you just say, okay, there's 3 in 35, and the next number after 3 is a 4. What's 3 times 4? That's 12. That's the first 2 digits in your answer. And then, of course, anything that ends in 5, you have a 5 times 5 involved, so you're going to get a 25 as the last 2. It works. Okay, so 3 times 4 is 12. 35 times 35. 3 times 4 is 12, and then I tag on a 25. If that really works, then I should be able to say 75 times 75. 7 times 8 is 56. So 75 times 75 should give me 56 and then a 25. It's a cute trick. I think it was a teacher who taught me that trick. Anyway, I know that this is 35 squared. So I can do my difference of squares. Took a long time for me to get around to it. Square root of x squared is x. Square root of 1225 is 35. I need a minus and a plus in whichever order. I think I'm going to put a plus first and a minus second. And then, of course, I can do verification by multiplication, but I'm not going to. What I'm going to do is move on to my last couple of examples of difference of squares because I'm watching the clock. And that means I'm going to have to peek at my clipboard again. And that's always been fun the odd time because it doesn't happen very often. You're multiplying a number by itself that's 2 digits and ends in 5. But sometimes you'll be somewhere and someone will say, I wonder what 85 times 85 is for some reason. And then you very quickly in your head say 8 times 9 is 72. It's 7,225, and they wonder how you did that without a calculator. And there's a lot of cool tricks like that that you can learn. Okay, another difference of squares that's a little different. A different difference of squares, if you will allow that. How about this one? Uh-oh. He's got a second variable. It's not a number over here. It's not a number here either. But it's a difference of squares. Because it's a difference, it's a binomial. And x squared is a square, and y squared is also a square. So it should work. Square root of x squared is x. Square root of y squared is y. 1 minus 1 plus. FOIL. X times x is x squared. X times y, that's xy. Negative y times x, that's going to give negative xy. And negative y times positive y is going to give negative y squared. These cancel, yes it worked, x squared minus y squared. Okay, so the fact that I don't always have a number here, that sometimes I have a different variable here, it can still work so long as it follows the rules. That it's a difference, and they're squares. That's another one. I better erase. I'm writing nice and big on purpose so that people can see it, but then I don't leave enough room to pop a second example into the position. So it's better to erase. Okay, the last one I have for difference of squares. How about this one? Okay, so now I have a number here, but I have a number, a combination of number and variable here. Is this a square? If the 9 is a square, and it is, and the x squared is a square, and it is, then that means 9x squared is a square. So that's a difference of squares. We know 16 is a square. What's the square root of 9x squared? Okay, slow down. The square root of 9 is 3, and the square root of x squared is x. The square root of 16, of course, is 4. 1 minus 1 plus. Do the FOIL so we can do our verification. 3 times 3 is 9, and x times x is x squared. 3x times 4, that's 12x. Negative 4 times 3x, that's negative 12x. Negative 4 times positive 4, that's negative 16. These cancel. We have 9x squared minus 16. We can do difference of squares. Difference of squares is fun. Anything will work. Even if it looks kind of complicated, so long as it's a binomial, the operator in the middle is a minus, that's a difference. The thing at the beginning and the thing at the end are both squares, it'll work. Let me pop one more example in. Little challenger example, if you will. How about 81x squared minus, what have I not used yet? 4. I haven't used 4. Y squared. Okay, so now I have a number and a variable in both positions, but it's a binomial and it's a difference. And 81 is a square, and 4 is a square, and x squared is a square, and y squared is a square, so I know it's going to work. 81 is 9 squared, and x squared is x squared. 4 is 2 squared, and y squared is y squared. 1 minus 1 plus. It works. 9 times 9, 81. X times x, x squared. 9 times 2, that's 18. X times y, that's xy. Negative 2 times 9, that's negative 18. We all knew that was going to happen. Y times x, that's also xy. Negative 2 times positive 2, that is minus 4. Y times y is y squared. These cancel, equal and opposite. 81 x squared minus 4y squared. Math is really fun when you're able to check your answer and make sure it's correct right away, right after you do it, and that's one of the reasons I like factoring. Okay, I'm going to stop recording for a little while, but I'll be back to do the second half of this lesson, which will happen right after I do this. I'll be back in 1 second from now. Okay, I'm back. And yeah, that was more than 1 second, and you could probably tell because I had to erase this and then draw it again, so it would look different. I'm interested in knowing, when I watch this video later, if the second half of the video has different lighting. Because in the meantime, it became dark outside, and it was still light out, but starting to get dark when I filmed the first half. Interesting, eh? Not very. All right, let's do a review. That's the next thing. We're going to do more trinomials. The factoring of trinomials is very important, and we need lots more practice. We were covering it last week. We're going to the same style. Quite a few examples. Let's get into it. X squared plus 9x minus 36. Now, the way I like to do this, if you'll remember, is I define as A, B, and C the numerical coefficients of the three terms in the trinomial. So the first term is the x squared. Its numerical coefficient is 1. And for all of the examples like this that I've been doing so far, it keeps on being a 1. And we don't use the a equals 1 part very much, not yet. But the b is a 9 in this case, and we need that for sure. And the c is a negative 36, not just the 36, the negative sign goes with it. And then we're asking that question. What two numbers multiply to give c and add to give b? So we have to think of all of the factors of c, the factors of negative 36. As I start doing this, I don't worry about the negative sign at first. I just think, okay, what are the factors of 36? What two numbers multiply to give 36? There are a lot of choices. 36 times 1 is 36. 18 times 2 is 36. 3 times 12 is 36. 4 times 9 is 36. And 6 times 6. So we have a lot of choices. But because it's negative 36, that means there's even more choices because we can have negative factors as well. And then we think, well, if we're multiplying two numbers to get a negative answer, we know the law of signs says that means one of the numbers must be positive and the other one must be negative. So I need two of those factors, one positive and one negative, that will multiply to give negative 36, but also will add to give positive 9. So let's think again of the factors. 36 and 1, I don't see how I'm going to get those to add to 9. I reject them. 18 and 2, they won't add to 9. 12 and 3 though, 12 minus 3 is 9. And remember, one of these numbers is positive, the other one's negative. It has to be that way. So it's either negative 9, not 9, negative 12 times 3, which gives negative 36, or it's positive 12 times negative 3, which gives negative 36. Now we're down to only these two choices. Which of these pairs of numbers adds to give positive 9? Well, clearly, the 12 and the negative 3 add to give positive 9. We get the x squared by multiplying an x with an x, so I can write those in. The answers are the 12 and the negative 3. So I'm going to put a plus 12 and a minus 3. It works. It always works. This one was a little tricky because 36 has so many factors. But if you think about the factors of c, whether c is positive or negative, and play around with all the pairs of numbers, you will think of the pair of numbers that work to multiply to give c, but also add to give b. Once you find the numbers that work for both of those rules, you have the right numbers and you have the right answer. And I feel so much confidence in this. We all know I can verify this by multiplying with the FOIL, so I will. First, x times x, that's x squared. Outside, x times negative 3, that's minus 3x. Inside, 12 times x, that's plus 12x. Last times last, 12 times negative 3, that is negative 36. Two similar terms. Minus 3x plus 12x combines into plus 9x. And we have the same trinomial we started with. It works. So yes, I went into a lot of detail because it's the first example like this from this lesson. But now I'm going to do a few more, and I'm going to do them a little more quickly. Next trinomial. X squared minus 2x plus 1. So this one looks a little tricky because, I needed to erase these. I'm going to keep the a equals 1 because all of these examples I'm doing right now have an a of 1. Numerical coefficient of the x squared term is 1. B is negative 2 this time, and c is positive 1. What two numbers multiply to give negative 2 and add to give positive 1? Well, there are not too many choices. And I have to say that over again. What two numbers multiply to give positive 1 and add to give negative 2? Let's get this right, Doug. Okay, there are not many choices. What two numbers multiply to give 1? There's only two pairs of numbers that multiply to give 1. 1 and 1, or negative 1 and negative 1. Now we're talking about whole numbers here. I don't want to try and get into decimals and fractions with this. Not yet, anyway. Okay, 1 times 1 is equal to 1, but 1 plus 1 is not 2. Negative 1 times negative 1 is equal to 1, and negative 1 plus negative 1 is equal to negative 2. So the numbers are negative 1 and negative 1. I like to write them down just as part of my process. Therefore, I put my two binomial brackets. I need the x and the x to create the x squared, and both of the numbers are minus 1, so I write minus 1. And then I verify. X times x is x squared, x times negative 1 is negative x, negative 1 times x is negative x, negative 1 times negative 1 is positive 1. Two middle terms combine because they're similar, x squared minus 2x plus 1. That's what I started with, it works. Okay, this process works, we're going to keep using it. I'm erasing the b and the c, I'm erasing the two negative 1s, I'm erasing the question, and let's move on. Let's see how many of these we can do. I have to keep an eye on the clock. Okay. What if it's not x? Every single example I've done so far has had x. What if we use a different variable? We know variables are just variables, they vary. You can use different letters besides x. What if we have a squared minus 7a plus 10? Okay, same question though. A is equal to 1. I'm not talking about this a, I'm talking about the numerical coefficient. The b is negative 7 and the c is 10. What two numbers multiply to give 10 and add to give negative 7? Well, if they add to give a negative number, at least one of them has to be negative. But if one of them is negative, the other one has to be negative because they're multiplying to give a positive answer. So now I know I need two negative numbers. And two negative numbers that multiply to give 10, well, there are not many choices. Negative 10 and negative 1, or negative 5 and negative 2. But obviously only negative 5 and negative 2 are going to work for the adding to give b. Therefore I write my answer, and it's an a instead of an x. That's not a very big change, is it? A minus 5, a minus 2. Do the FOIL to verify. A times a is a squared. A times negative 2 is minus 2a. Negative 5 times a is minus 5a. Negative 5 times negative 2 is positive 10. Similar terms, minus 7a plus 10. Same thing I started with, it works. It keeps working. Next one. Erase these. Erase these. Erase all of this. This is fun because we get good at it. The process just keeps working. And if you practice enough, you get really good at it, and then you're just always able to do it, and it just becomes a fun little puzzle because you have to answer that question about the two numbers that multiply this and add to give that. It's just fun. How about, oh, what if the numbers are larger? X squared plus 30x plus 200. Oof. Okay, A is still 1, B is 30, and C is 200. Okay. What two numbers multiply to give 200 and add to give 30? It's popping into my head right away, and I think it will happen with students as well after they practice. 10 and 20. They multiply to give 200. They add to give 30. And we have an extra clue that there's nothing but plus signs here. So considering negative numbers isn't very tempting. 10 times 20 is 200. 10 plus 20 is 30. 10 and 20 on my numbers. X plus 10. X plus 20. Do the FOIL just to make sure. X times x, x squared. X times 20, that's 20x. 10 times x, that's 10x. 10 times 20, that's 200. Make the chalk thing a little longer. Combine similar terms. 20 plus 10 is 30x. The best thing about this is being able to verify. You have complete control. If you're in a test and someone asks you to factor this, you know you got it right. This means you know. You don't wander away thinking, I wonder if I'm going to get that question right. I wonder if I will get the marks for that question. No, you know you're going to get it right. Okay. Another example. Next one I have. Here's a cute one. I always found this one a little bit fun because it's kind of confusing looking, but it's not a problem because the process works. X squared plus 4x plus 4. Huh, they're both 4s. The B and the C are both 4s. What two numbers multiply to give 4 and add to give 4, and then we think, oh, yeah, We knew that because every student at some point earlier in their math education realized, hey, 2 plus 2 is 4, but 2 times 2 is also 4. So the numbers are 2 and 2. And then we write our answer, 2 pairs of brackets, x plus 2, x plus 2, and then we verify with the FOIL, x times x is x squared, 2 times x is 2x, another 2 times x is 2x, 2 times 2 is 4, yes, this sure works, x squared plus 4x plus 4. We have what we started with, it is correct. Next one, can I come up with one that's hard to do? It gets to the point where it's hard to come up with a difficult example. It's hard to make it hard. That must mean that it's becoming easy. I sure hope it is. Okay. X squared minus 15x plus 56. Okay, the numbers are a little weird. B is negative 15, C is positive 56. Two numbers that multiply to give a positive number have to both be negative or both be positive, but if they're adding to give a negative number, it means they're both negative. We need two negative numbers. 56. Come on, we've all learned our multiplication tables. 56 rings a little bell in our brains. That's 7 times 8, or 8 times 7. So negative 7, negative 8. Yes, negative 7 plus negative 8 is equal to negative 15. Negative 7 times negative 8 is equal to positive 56. And we write our answer, x minus 7, x minus 8, and we do our FOIL. And if we practice it this much, we get this good at it. We get to the point where it just flows. Is this the same as this? Yes, it is. It is correct. Okay. Here's one. I'm going to do an easy one, and then I'm going to do another one that's also easy. And they're going to be very similar, but they're going to be different. I'm doing one of my what-if things. Okay, so first I'll write the easier one. X squared plus 4x plus 3. What two numbers multiply? Oops, I didn't erase these. Let me erase them. So it is good to remember when you finish an example and do the next example to erase your B and your C. Well, if you keep on writing them in the same place on your page, which students don't do, students just move further down the page. But when you're doing this on a chalkboard, I have a tendency to use the same spot. Okay, what's my B and my C again? 4 and 3. So, will I be able to get away with forgetting to erase these between this example and the next example? Let's see. Let's see the time. Okay, it's an easy one. Because the numbers are kind of small, it's all plus signs. What two numbers multiply to give 3 and add to give 4? 3 doesn't have very many factors. It has 3 and 1 as factors. We don't have to consider negative 3 and negative 1, not in this case. So it's 3 and 1. 3 plus 1 is 4. 3 times 1 is 3. So yeah, it was an easy one, wasn't it? X plus 3, x plus 1. Now I'm going to do my FOIL verification without writing it down. X times x is x squared. X times 1 is x. 3 times x is 3x. And x plus 3x is 4x. Yep, that works. 3 times 1 is 3. Yep. So I'm even doing my verification without writing it down, and it still seems to work really well. What about this one? Here, I'll put a squiggly line in between. Uh-oh. There are y's. It's not the same as taking away the x's and putting a's. The x's are still there, but now there are y's. And what a mishmash. Is this hard? Well, there's one thing about it that is good. Very good news. It kind of looks the same. All that's happened is we have this extra y squared here and an extra y in the middle. So, what else is interesting about this? When I asked the questions and do the ABC, I didn't have to erase. Because the B is still 4 and the C is still 3, so this still applies, which means 3 and 1. So how am I going to do this? I need the x and the x, and I need the plus 3 and the plus 1, but I need a y. So the only thing that happened because of this extra thing about the y's is that I just did it the same way that I did here, but I left a bit of room in my brackets because I need a y and a y. And that really is all there is to it. It seems like, oh no, it's going to be so much harder, and then it's not. It's not harder at all. It's like writing a couple of y's. That's not very hard. But I should do my verification, and this time I'll write it down. FOIL, first times first, x times x is x squared. Outside, x times 1y is equal to xy. I could write 1xy if I want. Inside, 3y times x, well that's going to be 3xy. And last times last, 3 times 1 is 3, but y times y is y squared. Similar terms, 1xy plus 3xy is 4xy. And so it turns out the extra letter doesn't make it harder after all. It makes you do one extra little thing that's not hard. But this whole part, the trick to doing it, ended up being the same. So we could kind of ignore the y until we got to the point of knowing our answer, and then just remember to put a y in at the end. It really isn't that much more difficult, is it? So let's do another one like that. And let's do it 2 examples, one with the extra letter, one without. Again. So this time I have to erase these. They're going to change. Okay, the easier version. Whoa, watch out, don't fall. Okay, x squared minus 9x plus 14. I guess I may as well write the other example right away. X squared minus 9xy plus 14y squared. Yep, that's all there was to it. A is 1, B is negative 9, and C is 14. What 2 numbers multiply to give 14 and add to give negative 9? They have to both be negative. They multiply to give a positive, but they add to give a negative, so they're both negative. 7 and 2, 14 doesn't have very many factors, does it? 7 and 2, negative 7 and negative 2 are the numbers I need. Doing verification without writing it again. X squared minus 2x minus 7x minus 2x plus minus 7x is minus 9x. Negative 7 times negative 2, positive 14. X minus 7 minus 2. Notice how I'm leaving a bit of space because I need to stick a y here and there. FOIL, x squared minus 2xy minus 7xy plus 14y squared. Combine similar terms. Not too bad, is it? It's really not too bad. I have a feeling the students are getting pretty good at this. And one of the fun things is you can make up your own questions if you want. Because if you just randomly create an A, B, and a C, well, it might not work out very well. But you don't have to randomly create them. All you have to do is decide what the answer is first. So you pick 2 binomials that you feel like multiplying together, and you multiply them together with the FOIL. Then you use the answer you got to that as your question, and then you practice the factoring method. So you have an infinite number of examples to practice with. Look at the time. I think we're pretty much at the point where I can move on to one more thing. And I'm going to do 3 examples, probably only 3, but I'm going to do them slowly. Because we have another what if. And I think the students are ready for this what if. It's going to be more trinomials. And that means I don't want to erase all this stuff. I'm going to erase my B and my C and those little answer there, but I'm also going to erase my A. Because the what if is, what if A is not 1? all the examples we've done so far had a equal to 1. And I'll remind you that I started this lesson with some examples of common factor. One of the easiest factoring methods. Common factor is useful. I'm only saying that for, I don't know, my own hidden reasons. How about 2x squared? So a is not 1, it's 2. I'm taking baby steps. I don't want to start having all sorts of crazy numbers. 2x squared instead of 1x squared. Plus 11x plus 12. I'm doing the same thing to start with, except a is not 1, it's a 2. B is 11, C is 12. But I need one more thing. I'll move this. Just writing it lower. Two numbers that multiply to give and add to give are the same. I just needed some space. And they're adding to give B. That's the same, but something is going to change. What we need to do is we have to find AC. AC, as you know, if you understand math and variables and stuff, is A times C. So what's A times C? That's 2 times 12. AC is 24. So we have a fourth value to find when we do this step. And when we find our two numbers that multiply to give, not C, multiply to give AC, but they still have to add to give B. So a couple little things change, but not very much. But I still have to answer the question, don't I? That little puzzle is the same now. What two numbers multiply to give 24 and add to give 11? And that should be pretty fast. Because notice how, again, I only promoted this to a 2. I didn't go crazy with that, and I also put plus signs. I'm keeping this quite simple. So two numbers, and we know they're going to be positive. They multiply to give positive 24. They add to give positive 11. What are the factors of 24? 24 and 1. We all know the answer. I know you already know the answer. 24 and 1, 12 and 2. Does 3 work? Yeah, 3 and 8. Yeah, ding, 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 ding. And 4 and 6, of course. But 3 and 8 is giving that ding, 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 ding because 3 plus 8 is equal to 11. That's a comma. I don't know if it looks like one. It's a comma. 3 and 8. And now, okay, so a couple little things changed, but a lot of stuff is the same. And that happens here too. There's going to be a couple little changes. What I like to do is rewrite this, but I replace the 11 with bracket. And then inside the bracket, I have to put 3 plus 8. Those two numbers that were my answer. 3 plus 8 instead of 11. Because of course, 3 plus 8 is 11. So when you look at this, you realize I haven't really changed this. It's still 11. But then I can do the distribution thing. Is this distribution backwards? Yes. The distribution thing means I can say 2x squared plus 3x, because the 3 is being multiplied by the x, plus 8x, because of course the 8 is also being multiplied by the x, plus 12. I now have a 4-term polynomial. And the way I deal with this is I use common factor in the first half, and I use common factor in the second half. So the greatest common factor of these two terms is x. And when I factor it out, I get 2x plus 3. The greatest common factor of these two terms is 4, and I'll write plus 4, because I have to give it sign. So it's going to be plus 4. And when I factor a 4 out of these two terms, I end up with 2x plus 3. What happens in the bracket is the same. If you did this correctly, what happens inside the bracket will be the same. And if you know your distribution, you realize, oh, I can rewrite this if I want. X and plus 4 can all be written together. And then I just have to write the 2x plus 3 once, because this line really means the same thing as that line. And we have our answer. So it is a little different. How much time do I have left? Do I have time to do two more examples? I hope so. Let's do the FOIL though and make sure that this does give me 2x squared plus 11x plus 12. X times 2x, that's 2x squared. X times 3, that's plus 3x. 4 times 2x, that's plus 8x. 4 times 3, that's plus 12. We are not surprised to see this happen, are we? So this one had a bit more steps, but a lot of the steps were the same. And it's really not hard, you just have to practice it like anything else. I'm only introducing 3 of them, and I'm keeping them all quite simple. I'm keeping using 2's and plus signs to just get a taste of what this is like. But I have a couple more, and I'm going to try to do them, and I'm going to have to do them fairly quickly because of the time constraint. So I'm erasing all of these values, and these, and this whole thing. Second last example for the lesson. 2x squared plus 16x plus 30. A is 2, B is 16, C is 30, AC is 2 times 30, AC is 60. What two numbers multiply to give 60 and add to give 16? What two numbers multiply to give 6? Oh, 10 and 6. 10 and 6. It's working. Yes, it is. 10 times 6 is 60. 10 plus 6 is 16. So what's that procedure again? Put a bracket here. Write 10 plus 6 inside it. And if I wrote 6 plus 10, it would still work. 2x squared plus 10x plus 6x plus 30. More chalk, please. Common factor of these first two terms is 2x, which will leave me an x plus 5. Common factor of these last two terms is 6, which will leave me an x plus 5. Rewrite it as 2x plus 6 together in a bracket, and x plus 5 written only once, and we are done. I'm not going to do the verification because I want to do that last example. (2x squared plus 15x plus 7). A is 2, B is 15, C is 7, AC is 2 times 7, that's 14. What two numbers multiply to give 14 and add to give 15? That's going to be 14 and 1, isn't it? Rewrite this with a bracket. Write 14 plus 1 or 1 plus 14 in there. It works either way. Rewrite it like this. Does it look tricky? Greatest common factor of these is 2x, leaving x plus 7. Uh-oh. Greatest common factor of these is 1. You have to find one. So since they don't have a common factor, but they can both be multiplied by 1, well, they have a common factor of 1. Normally that would be pointless to say, but it's useful here because it allows us to finish answering our question. 2x plus 1 and x plus 7 only written once is my answer. I am done. This method works. Just like the other methods, you have to practice it. That puzzle is fun. I think that's really the last thing I need to say in this lesson, is that this little puzzle, let two numbers multiply to give this and add to give that. That's fun. I have fun. I've been doing this for many years, and I still find it fun. So I hope the students find it fun as well. I look forward to continuing to teach you more factoring and more polynomials and more math the next time. Until then, happy math.